Okay, hello, my name is Nick Anderson, and today I'm going to be giving you a little demo about the framework I developed for the Spring 2014 Digital Forensics class final project. Today is May 4th, 2014. It's 12:37 p.m. It's like 60 degrees out in beautiful New York City. So I designed this project to aid in forensic analysis and forensic investigation. The idea was that sometimes you might be locked out of an account, you're waiting on encryption crackers or something along those lines. This project, reaPyr, is designed to try to go out to a specified disk image and harvest or aggregate as many different credential sets as it can possibly find. Currently, it supports only Windows XP. It's only been tested on Windows XP. It should work in Vista Plus kernels. However, I haven't had the opportunity or the capabilities to test those types of images. Although I have tried to write this out with all of the correct file structuring, so that way you should be able to throw a Vista or a 7 image at it and it should work. To get started with reaPyr, you can go out to my GitHub repository, which is github.com poppyseedpleasure, as spelled right here, and you pull down the reaPyr.git. Just go pull down everything that you need. As it's Python, there isn't any installation that it needs. You simply need to make sure that you have Python 2.7 and the PyTSK3 framework. So if you can go Python and import PyTSK3 and it works successfully, you should be good to run reaPyr. So taking a quick look at the structure of reaPyr, the way that reaPyr works is we have this reaPyr.py file in the root repository. This is kind of the overarching manager that runs each individual reaPyr file, which are located in Windows, Google, IM, Mozilla at the moment. There will be more to come at some point. And all of these make use of a file or a class structure that I developed called disk. And disk simply is an abstract representation of a given disk image. And it allows us to very easily carve out directories or files from a specified image. Currently, reaPyr supports just any disk image that TSK will support. So if TSK can run on it, you should be good to use reaPyr. We're going to look at that later. Sorry about that. Sneak previews. To run reaPyr, you can simply run Python and reaPyr. It'll give you this little help message, and you can run it with the -h to get a little bit more detailed help. All that you really need to specify to get running is the disk name. However, we also have options for you to specify the offset for where the partition is and the sector size, and we'll talk about that a little bit later. So I've developed a couple of test images just specifically for use with this case. So we have WinXP sample 1 and sample 2. These disk images are Windows XP SP3, and they have a couple of user accounts, and each user account is using multitude of web browsers and IM, so like they have Skype and Pigeon Instant Messenger and IE8, and Chrome and Firefox, I think, are the latest versions as well. Yeah, so let's go ahead and give it a run. To run reaPyr, you do Python reaPyr with a tick D and then the path to the test image that you want to run it on. So we'll go ahead and start out easy and take a look at the WinXP sample number 1. And if reaPyr just runs and has no issues and you don't see any errors printed, then that's how you know that everything went successfully. If you see an error message, this will kind of indicate that something's wrong, and it should give you some verbosity about where the problem is, at least in the code base. So once you have a successful run of reaPyr, if you do a quick check at your directory, you'll see that you have a few new folders and files generated. We have this disk rec, this harvest directory, and lastly a report.csv. Report.csv is a comma-separated file that tells you specific information about every file that was recovered by reaPyr. Specifically, each of these reaPyr files, like Google, IM, and Mozilla, they go out to the disk image and they extract some very, very specific files that they need for their credentials, and they dump them into this disk rec folder. And then the main reaPyr file will take anything in this disk rec folder and it will write out the report and move those files to the harvest folder. So if we take a quick look, this is the primary reaPyr functionality here. You see that this starts out in its main reap function by creating this disk image. This is, as I mentioned earlier, the abstract disk structure that represents the image that you've specified. and then it proceeds to call each of the individual reapers. So it does a report given the data from WinReap, and it does a report given the data from Google Reap, and the clean function is what aggregates everything into that central harvest folder that I showed earlier. And this is just a quick look at what a reaper looks like. Each of these reaper files, I guess I'll show you the directory for these. If we go and we take a look inside of the Windows reaper file, you see that they're supposed to be as self-contained as possible. So we have a winreaper.py and an init.py. The init.py allows the primary reaper class to call this winreaper function, and this winreaper function is what we're looking at here. At its most base level, it's just a Python program that has a reap function, and the reap function is purely designed to just like go out and look for some really specific files on this disk image that it's been handed and try to carve each of those out, as you can kind of see this happening here. And then, like in this specific case, it's creating a report of some of the recovered files that it found. Okay, so let's go and look at some of the fun stuff, because this is getting kind of boring. If we go into the harvest directory, or actually better yet, let's start by taking a look at the report and kind of get an overview of what we found. Cat out the report file, you see that we have comma separated, as I mentioned earlier, and it tells you like what reaper it was that found it, the name of the file that it carved out, as well as the SHA-1 sum, and lastly a file size and a short description about what that file actually is. So like this first line, you see this is a Windows SAM database. It's a registry database used by Windows XP to store user account credentials. Kind of boring. I mean, it's got some good stuff, but something like this guy might be a little bit more interesting. Windows reaper wincredsdump.txt, and this is a credential hash dump of the Windows account. So let's go check him out. So as it's mentioned in the report, it was reaped by Windows. So if we see to harvest Windows, this is where all of the Windows reaped files are, and you can see it's right there. Cat wincredsdump, and we see this program is developed. This is a program called creddump.py, and it's attributed inside of the Windows code, and as well as on my GitHub repository. So you can use it individually, but all it does is it takes these Windows registry files and it gives you the hash dump of the passwords. So you can see administrator and the group ID and the actual hashed NTLM hash password, as well as like the LSA secrets. There's also a section that isn't depicted here that is the cached passwords in the Windows XP box. However, there weren't any cached passwords, so it doesn't write that part out because it's just extraneous. Something else that's worth noting that I thought was pretty cool, if we actually cat out that report again, sorry about that, cat out that report again, we see that there's a file from the Pigeon Reaper. It's called Administrator XP Accounts. This Pigeon Reaper actually lives inside of the IM Reaper, and that's just kind of a mess up on the name that I'll be fixing at some point when I figure out a better design for it. And if we look inside at what that Pigeon file actually is, we cat administrator accounts, we see that Pigeon doesn't actually encrypt any cached credentials that it stores on your disk. So if you use Pigeon IM to log into like Facebook Messenger, MSN Instant Messenger, Gmail, or Hangouts, Pigeon just stores things in clear text. So you can see here we have a protocol purple messenger. That's what Pigeon calls each of its account blobs. It's a purple file or something like that. But you see that we have just clear text name and password right here. So if you're perpetrator, or if the person that you're investigating is using Pigeon, you're kind of in the money. Yeah, so that's some of the cooler parts of functionality that we have. Another feature about this is that it does aggregate reporting. So if you run this program, if you run reaper across multiple disk images, you shouldn't have to like back up your report before you run it on the next one. It'll just append it with some new line separation. So for instance, if we run Python on, let's do disk image, oh sorry, it's not disk image 3, it's this one of these images that we used in the digital forensics class. So we have Joe 2009. This was one of the case files that we had for an investigation. It's part of our midterm, and if we just run it, we have a slide issue. Just didn't find it. Test images. Sorry, bear with me. Get it running. Oh, I'm misspelling things because I'm super great like that. So we run it and we see right off the bat that reaPyr has a problem opening it. But if you take a quick look at what the stack trace is, what's happening here is just that the sleuth kit framework is having some difficulty finding where the offset, it can't tell what the system type is. So you can use tools like MMLS to find out where the offset is for the NTFS file permission, and you see that it starts at offset 63, so we can go back to running reaPyr and we can provide it an offset of 63, and you see now like it's actually doing its job, it's working. So one thing that you might notice here is that it's taking a little bit to run. This is due to the fact that the Firefox reaPyr is currently developed and it's in kind of an ugly manner. It's still kind of undergoing construction. It works, it gets the job done, but it's not very pretty. As you can see here, we have some pretty poor design, just in the sense that it's pulling out very unique databases based off of the Firefox version. So it's looking for some of these legacy Firefox databases. The primary database that it's trying to get, though, is this key3 database, which it successfully gets. And see that now that we're done, we can cat out report again. And you see here was the report from the first run, and then here's the report from the second run. So it goes out and it finds some of these other files, like joe_nt_user.dat. So we definitely know that it's working on the disk image we specified, as well as like a key3 database. Lastly, I had an image that had quite a few more users that I thought was a little bit more interesting, because we pull so much more extra data. So we run it on this WinXP sample 2. This has 3 different user accounts, and they've all got cached and stored credential files. So if we again cat out that report, you see there's a whole wealth more of data that it finds here. We have a whole bunch of Skype credential databases. These are encrypted, however they're still clear text encrypted, or files with the baggins. It's a clear text file, and the actual credential part is this big, encrypted blob. So which you can now research a little bit further into how Skype does its credential encryption, that you can hand this off to some sort of a Skype cracker kind of a thing. We also have this cached key. So between these two things, you should be able to hopefully break the encryption. Okay, that's it. Please let me know if you have any questions. My email is on the GitHub repository, and thank you very much for your time.